There we go. Hi, everybody. I'm Dave Aronson, the T-Rex of Codosaurus, and I'm here to teach you to kill mutants. So, what on Infinite Earths makes mutation testing different from all the other software testing techniques? Oops, slides got ahead of me a bit. The main difference is that most of the others are about checking whether or not our software is correct. But mutation testing assumes that our code is correct, at least in the sense of passing its tests. Instead, mutation testing checks two other qualities. In a typical code base, I think the more important one is that our test suite is strict. Now, you might think that's what test coverage is for, but no. The only thing that test coverage tells us is that at least one test ran the code that it claims is covered. It tells us nothing about whether the correctness of the code made any difference to whether any test passed or failed. And that's what tested really means, right? So how can we tell if our code really is tested? That's where mutation testing comes in. To check that our test suite is strict, a mutation testing tool will try to find the gaps in our test suite that let our code get away with unintended behavior. Once we find these gaps, we can close them by either adding more tests or by expanding and improving existing tests. Lack of strictness usually mainly comes from lack of tests, of course, but also from poorly written tests. The other thing mutation testing checks for is that our code is meaningful, so that any tiny little semantic change to the code will produce a noticeable change in its behavior. Lack of meaning usually comes mainly from code being redundant or unreachable or otherwise just not having any real effect. When we find meaningless code, the usual fix is to just remove it. Mutation testing puts these two together by checking that every change to the code that the tool knows how to do does make a noticeable change to its behavior, and that the test suite is strict enough that at least one test will notice that change and fail. Now that's the positive side, but there are some drawbacks. As Fred Brooks told us back in 1986, there's no silver bullet. Okay. The first drawback is that it's rather hard labor on the CPU, and therefore usually rather slow. We certainly won't want to mutation test our entire code base every time we save one file. Maybe over a lunch break for a small system or a weekend for a large one. Fortunately, though, most of the tools let us just check specific functions, classes, files, and so on. Plus, they usually include some kind of incremental mode so that we can check just the changes since the last mutation test or the last Git commit or the changes from the main branch or some other such milestone. With filtering like that, maybe we can test just the relevant changes on each save, or at least over a much shorter break. Another drawback is that it's often not at all clear what to do about the results. It tells us that some particular change to the code made no difference to the test results, but what does that even mean? It takes a lot of interpretation to figure out what a mutant is trying to tell us. They're usually trying to tell us that our code is meaningless or our tests are lax, or both, but it can be very hard to figure out exactly how. Even worse, sometimes it's a false alarm because the mutation didn't make a test fail, but it didn't make any actual difference in the first place. And it can still take quite a lot of time and effort to figure that out. Now that we've seen some of the pros and cons, what does mutation testing actually do? It mutates copies of our code, hence the name. And it does this to create test failures, also known as faults. So mutation testing can be classified as a fault-based testing technique, and this means it's related to something you might already be familiar with, Chaos Monkey from Netflix. But the way mutation testing works is sort of upside down from what Chaos Monkey does. Chaos Monkey is best known for injecting faults into Netflix's production network. If all still goes well, in the sense that Netflix's customers don't notice and their metrics still look good, then Netflix knows that their error recovery is working fine. Mutation testing, however, injects semantic changes, not necessarily problems. We hope each of these changes will create faults, but that depends on the test suite. It injects them into copies of our code, not our actual network. And it does this in our test environment, not production. And if everything still goes well, in the sense that our tests all still pass, that doesn't mean all is well. That means that there is a problem. Remember, each change to our code should make at least one test fail. So how does this actually work? First, the tool breaks our code apart into pieces to test, usually our functions. Then for each one, it makes mutants from that function. And to do that, it looks closely to see how it can be changed. And for each way, the tool makes one mutant with that one mutation. And once our tool is done creating all the mutants it can for a given function, it iterates over that list. And now we get to the heart of the concept. This chart represents the progress of our tool. Most of them don't give us anywhere near all this info, let alone so neatly organized, but it's a useful conceptual model. For each mutant derived from a given function, the tool runs the function's tests, but it runs them with the current mutant in place of the original function. If any test fails, this is called killing the mutant, and it's a good thing. It means that our code is meaningful enough that the change the tool made in order to create this mutant made a difference in the function's behavior, and at least one test noticed that difference and failed. Then the tool will mark that mutant killed, stop running any more tests against it, and move on to the next one. Once a mutant has made one test fail, we don't care how many more it could make fail. Like so much in computers, we only care about ones and zeros. On the other claw, if a mutant lets all the tests pass, then the mutant is said to have survived. And that means that the mutant has the superpower of mimicry, skilled enough to fool our tests. This usually means that our code is meaningless or our tests are lax, or both. And now it's up to us to figure out how. Now let's peel back one layer of the onion and look at some technical details of how this works. First, our tool parses this code, parses our code, so this code, which you don't really need to read and understand, becomes this abstract syntax tree, which you also don't really need to understand except to notice that it includes some function definitions, one of which I've fleshed out in full. Then it traverses that tree looking for subtrees or branches, if you will, that represent each function. And from each one, it makes mutants. To make mutants from an AST subtree, it traverses that subtree just like it did to the whole thing. But now, instead of looking for even smaller subtrees it can extract, like twigs or something, it's looking for nodes where it can change something. And each time it finds one, and for each way it can change that node, it makes one copy of the function's AST subtree with that one node changed in that one way. Now I've been talking a lot about changing things, so what kind of changes are we talking about? There are quite a lot. You could change a mathematical, logical, or bitwise, or whatever other kind you have, operator from one to another. When the order of operands matters, it could swap them. It could change a comparison from one to another. It can remove an if condition or a looping condition. It could replace a function's entire contents with just returning a constant or any of the arguments or raising an error or nothing at all. It could change a value to some other value, even changing it to an incompatible type, such as changing a number to a, if I may quote Smeagol, string or nothing. There are many, many more types of changes. but I trust you get the idea. Now, there's no more low-level details I want to add right now, so let's finally walk through some examples. We'll start with an easy one. Suppose we have a function like so. Never mind why, it just makes a good simple example. Think about what a mutant made from this might return. Mainly, it could return results such as any of these expressions or constants, and many more, but I had to stop somewhere. Now, suppose we had only one test, like so. This is a rather poor test, and I think at least one reason why is clear to most of us, but even so, most of those mutants would get killed by this test, the ones shown here in crossed out green. The ones returning constants are very unlikely to match. There's no particular reason the tool would put a 4 there as opposed to 0, 1, -1, and other such significant numbers. Changing the exponentiation into subtracting one argument from the other gets us 0, dividing them gets us 1, returning either one alone gets us 2, and the mismatched types and deliberate errors will at least make the test not pass. But addition, multiplication, and exponentiation in the reverse order all get us the correct answer. So mutants based on these mutations will survive our test. This is the usual way mutants survive, by returning the same result as the original function. Or they have the same side effect, whatever it is that our tests are looking at. Now, to determine how this happens, it helps to take a closer look at one along with the test it passes. Let's start with the plus mutant. Looking at this change together with our test makes it clear that this one survives because 2 plus 2 equals 2 to the 2. And so does 2 times 2, but he's in the background. We can save him for later. So how can we kill this mutant? In other words, make at least one test fail when run against it that would pass when run against the original code. To do that, we need to make at least one test use inputs such that x plus y is different from x to the y. For instance, we could add a test or change our existing test to assert that 2 to the 4th power is 16. All the mutants that our original test killed, this would still kill. But also, 2 plus 4 is 6, not 16. So this kills the plus mutant. I hope you see how that works. But better yet, 2 times 4 is 8, which is also not 16. So this kills the times mutant as well. Killing one mutant often kills many other mutants from the same function. But the pair of argument swapping mutants survive because 4 squared and 2 to the 4th are both 16. But we can attack those mutants separately. No need to kill them all in one shot and be some kind of superhero about it. To kill these, again, we can either add a test or adjust an existing test to do something like assert that 2 to the 3rd power is 8. 3 squared is 9, not 8. So this kills the argument swapping mutants. And better yet again, 2 plus 3 is 5, 2 times 3 is 6, and both of those are not 8. So the plus and times mutants stay dead. We don't get any zombie mutants wandering around, even if this were still our one and only test. With these inputs, the correct operation is the only simple common one that yields the correct answer. This isn't the only solution, though. There are lots of ways to skin that flurkin. Now, this may make mutation testing sound simple, but this was a downright trivial example. So let's look at a more complex one. Suppose we have a function to send a message, like so. Send message uses send bytes to send as many bytes as send bytes could send, kind of like a woodchuck, looping up where it left off until the message is all sent, a very common pattern. A mutation testing tool could make lots and lots of mutants from this, but one of particular interest would be this, an example of removing a looping control. Now suppose that this mutant does indeed survive our test suite, which consists mainly of this. There's a bit more that I'm not going to show you quite yet, dealing with setting the size and actually creating the message. But even without seeing that test code, what does the survival of this non-looping mutant tell us? If a mutant that only goes through this loop once acts the same as our normal code as far as our tests can tell, that means that our tests are only making our normal code go through that loop once. So what does that mean? You'll find that interpreting mutants often involves a lot of asking yourself, so what does that mean? Often deeply recursively. But in this case, it means we're not testing sending a message larger than send bytes can handle in one chunk. There are many ways that can happen, but we're only going to look at two possibilities. The most likely is that we simply forgot or just didn't bother to test with a big enough message. For instance, suppose our maximum chunk size, what send bytes can handle in one chunk, is 10,000 bytes, but we're only testing with a little 3-byte message. The obvious fix is to deliberately use a message larger than our maximum chunk size. And with this kind of fake messaging, we can easily construct one like so. But now let's take a look at another possible cause and solution. Maybe we did test with the largest permissible message out of a set of predefined messages, or at least message sizes. For instance, here we have small and large message sizes. We tested with a large, and yet this mutant survives. In other words, we're still sending the whole message in one chunk. What could possibly be wrong with that? It sounds like a good thing to me. What is this mutant trying to tell us in this case? In this scenario, it's trying to tell us that a version of send message with the looping removed will do the job just fine. If we remove the looping, we wind up with this, and if we run our mutation testing tool on this, it'll show some other stuff as now being redundant because we only needed it to support the looping. If we also remove that, lather, rinse, repeat, then it boils down to this. And now the message is clear. The entire send message function may well be redundant, so we can just use send bytes directly. In real-world code, though, maybe not, because there may be some logging or error handling and so on that we need to have in send message and can't push down the stack into send bytes. But at the very least, the looping was redundant. Fortunately, when it's this kind of problem, the usual solution is clear and easy. Just rip out the extra junk that the mutant doesn't have. This will also make our code more maintainable by getting rid of useless cruft that just gets in the way of understanding it. Now that we've seen some examples of finding both bad tests and redundant code, I'll address a couple of frequently asked questions. First, this all sounds pretty weird, deliberately making tests fail to prove that the code succeeds. Where did this whole bizarro idea come from? Mutation testing has a surprisingly long history, at least in the context of computers. It was first proposed in 1971 in Richard Lipton's term paper, Fault Diagnosis of Computer Programs at Carnegie Mellon University. But the first tool didn't even appear until 1980 in Timothy Budd's PhD work at Yale. But it was just not practical on typical computers of the day until about the early 2000s, with significant advances in CPU speed, multi-core CPUs, and so on. But now it's practical even on fairly low-end but modern systems like this 2020 MacBook Air that I'm presenting on right now. Another common question is, where should we fit this into our development process? Mainly, I think it belongs at least here as part of the requirements for a pull request or whatever your process uses to be approved. You can set some standards for what you're willing to tolerate on the changed code or the whole code base or both, like a number of surviving mutants or an allowable % increase in them, ideally 0. Ideally, this would all be automated as part of a CI pipeline. That said, I would personally also do it in my own work as part of the linting step, where I apply all sorts of quality checking tools, style checkers, and so forth. If you'd like to try mutation testing for yourself, here's a list of tools for some popular languages and platforms, and some other ones. I doubt many of you are doing Fortran 77 these days, including, of course, Python. The tools I know are outdated are crossed out. To summarize at last, mutation testing is a powerful technique to help ensure that our code is meaningful and our tests are strict. It's easy to get started with, but it's not so easy to interpret the results, nor is it easy on the CPU. Even if these drawbacks mean it might not be a good fit for our current projects right now, I still think it's just a really cool idea in a geeky kind of way. If you have any questions, we have about 4 minutes for them. And if you think of anything later, there's my contact information, plus the URL for the slides, complete with a full script, which I've mostly stuck to. So, any questions?